An earthquake is a release of energy due to tectonic plates moving relative to each other through conversion, diversion, or sliding past each other. Behind me, you can see the earthquake in Chile in 2010, which was an immense 8.8 on the Richter scale. The socio-economic impact was massive, as 2 million people were affected and $30 million were lost. Due to the magnitude of the earthquake, the horizontal peak acceleration, the X and Y planes, were large and lasted long periods, which created significant damage to buildings such as the O'Higgins Tower, as seen in the picture. The east and the south face were affected the most, and diagonal shear cracks on columns were seen on the south face. The building lost a partial story at the location of the frame setback, as seen in C, and suffered significant damage to the coupling beams, as seen in D. 3D surface modelling showed that 20% of the concrete and brick on the south face had spalled, cracked, or fallen off. This occurred due to increased vulnerability to lateral forces due to vertical irregularities and lack of lateral stiffness. By creating a model of a seismic resistant building using straw and blue tack, we made strong columns to make an adequate lateral load resisting system and used strong vertical connections between those columns and a foundation. We created vertical beams and a concentrically braced frame and used irregular symmetrical shapes to reduce any setbacks. Our building survived the earthquake, however, we needed stronger connections between the columns and the beams on the top floor, and due to the lack of it, allowed our vertical beam to move freely. We also had a massive irregularity due to the use of more material on the west surface of our structure. Earthquakes also result in landslides and liquefaction, which is when, due to the accumulation of cyclic loadings, the saturated sandy soil starts behaving like a fluid. Seen in the picture of the Las Palmas Dam in Chile. The soil, initially densely packed, experienced vertical and horizontal acceleration, and combined with the undetected groundwater, this created seismic liquefaction. In the top left equation, Fs denotes the factor of safety of a slope, which is dependent on the cohesion of the soil, the length, as well as the normal and shear forces on the slope. In the diagram, the earthquake is modelled as two static forces in the horizontal and the vertical components. This is called pseudostatic slope analysis. Using the variables in the diagram help us figure out the factor of safety. The equations here show how that relates to the stability of the slope. During the second workshop, we modelled a slope using granular sand and applied an external lateral force to mimic an earthquake of a measured acceleration. We calculated tan phi and tan beta, which is the angle of the slope before and after the earthquake correspondingly. What we found was as acceleration increases, the angle of the slope decreases. To find the minimum inclination of a slope with a factor of safety of 1.2 in that zone of Chile, we use this. As the dam falls in zone 2 of Chile, the acceleration uses 0.3 g, and reading from the graph, the angle of slope here is 24 degrees. Using the calculation seen, we get 28.1 degrees. By using these ideas and calculations, we are able to reduce vulnerabilities of the as-built environment and provide the two principles of seismic design: saving lives and reducing economic impact, creating a better standard of living for everyone.